Welcome to this session on clustering as part of SAP BTP AI best practices. We'll explore how to efficiently identify patterns in data using SAP HANA machine learning tools. By the end of this session, you'll have a clear understanding of the key principles, best practices, and implementation approaches for clustering modeling. Our discussion will follow these four key steps. First, we'll provide an overview of clustering and its benefits in the SAP ecosystem. Second, we'll cover the essential prerequisites you'll need to have in place, including supported environments and required components. Third, we'll explore key choices and guidelines that impact your implementation, including modeling valuation to understand how well a model is performing, therefore helping to identify areas for improvement and guide model selection. Finally, we'll dive into implementation approaches across programming models, providing concrete examples for Python. Clustering aims to partition a dataset into subsets, also called this clusters, such that data points within the same cluster exhibit high inter-cluster similarity, which points in different clusters exhibit while points in different clusters exhibit low inter-cluster similarity. The results of clustering is a set of labeled groups that reveal underlying structure in the data, providing valuable insights for decision-making, pattern recognition, and anomaly detection. In the SAP ecosystem, this involves leveraging SAP HANA machine learning tools, specifically Predictive Analysis Library and HANA ML. The outcome of a clustering process is a set of groupings called clusters, where each data point is assigned to one cluster based upon similarity. The goal is to discover natural groupings and data without using labels. Why use SAP HANA machine learning for clustering? There are three main benefits. First, algorithm interchangeability. You can easily switch between different algorithms like k-means, density-based spatial clustering of application with noise, a glomerate hierarchical clustering, spectral clustering to best suit your specific needs. Second, out-of-the-box features that supercharge your development with built-in capabilities such as data processing algorithms. Third, security and SAP ecosystem integration. It's fully integrated with SAP technologies, leveraging enterprise-grade security and native in-database processing. These advantages make clustering more efficient and accessible for SAP users. Before implementing clustering solutions, let's cover the necessary prerequisites. You'll need SAP HANA Platform 2.0 SPS 04 or higher, or preferably SAP HANA Cloud for easier management. Sphere or Express Edition can also be used for specific areas. Application Function Library containing Predictive Analysis Library and Automated Predictive Library components. SQL script enabled for executing machine learning algorithms to provide more context. SAP HANA is an in-memory database enabling real-time analytics and applications. The HANA ML libraries, Predictive Analytics Library, and Automated Predictive Library provide native in-database functions for predictive analysis and machine learning. Script Server is an auxiliary HANA process essential for executing these machine learning functions. Setting up these prerequisites establishes a strong foundation for implementing effective clustering solutions at scale. Let's examine the high-level reference architecture for clustering using SAP HANA machine learning. The diagram shows the complete machine learning execution environment within the SAP HANA ecosystem. At the core is the SAP HANA database hosting Predictive Analysis Library and Automated Predictive Library. These provide the core clustering algorithms. This architecture ensures efficient, scalable, and secure clustering while leveraging the performance advantages of in-database processing. Let's discuss key choices that impact the performance of your clustering scenarios. Effective data preparation is crucial for quality clustering analysis in SAP HANA machine learning. Key guidelines focus on three strategic areas. First, implementing a clear no policy. define a strategy for handling missed values, as many predictive analysis library procedures are bored on nulls. SAP HANA Machine Learning offers tools like the inputter within predictive analysis library. If providing methods like mean or median imputation, second, focus with features important analysis. When data has many features, some will be more useful than others for clustering. Use predictive analytics library techniques like feature selection or permutation importance to identify the most relevant features for clustering. This reduces noise, combats the curse of dimensionality, and improves accuracy. Third, simplify with dimensional reduction. For high-dimensional datasets, use techniques like principal component analysis to reduce the number of features while retaining essential information. This can reduce noise, speed up training, and improve detection accuracy. Systematically applying these techniques, number policy, feature importance, and dimensionality reduction enhances clustering in SAP HANA. SAP HANA Predictive Analysis Library offers a wide range of clustering algorithms. Choosing the right clustering model in SAP HANA Predictive Analysis Library depends on several key factors related to both the characteristics of your data and the business problems you're trying to address. Some of the commonly used algorithms are as follows. K-means algorithm partitions and observations or records indicate clusters in which each observation belongs to the cluster with the nearest center. Density-based spatial clustering of applications with noise is a density-based data clustering algorithm. Finds a number of clusters starting from the estimated density distribution of corresponding nodes. It requires two parameters, skin radius, and a minimum number of points required to form a cluster. It provides a method to automatically determine these two parameters. You can choose to specify the parameters by yourself or let the system determine them for you. Agglomerate hierarchical clustering is a widely used clustering method which can find natural groups within a set of data. The idea is to group the data into a hierarchy or a binary tree of the subgroups. A hierarchical clustering can be either agglomerate or divisive, depending upon the method of hierarchical decomposition. An advantage of hierarchical clustering is that it does not require the number of clusters to be specified as the input. And the hierarchical structure can also be used for data summarization and visualization. Spectral clustering is an algorithm evolved from graph theory and has been widely used in clustering. Its main idea is to treat all data as points in space, which can be connected by edges. The edge weight between 2 points further away is low, while the edge weight between 2 points closer is higher. Model performance metrics are crucial for evaluating and comparing the effectiveness of machine learning models. They provide a quantitative measure of how well a model is performing, helping to identify areas for improvement and guide model selection. Common metrics specific to clustering include silhouette, a model used to validate the cluster of data. The computational complexity of silhouette is big O of n squared, where n represents the number of records. When n is very large, silhouette costs a long time. Considering the efficiency, SAP HANA Predictive Analytics Library provides a lighter version of silhouette called slight silhouette, where -1 stands for the poor clustering results, and 1 stands for good results. Let's discuss implementation guidelines for selecting your programming model. For data science workflows, we recommend using Python with the HANA ML library, providing a streamlined, intuitive experience aligned with standard data scientist practice, including convenient data manipulation and integration with machine learning workflows. For alternative approaches, consider SQL script to directly call predictive analytics library procedures when tight integration with SAP HANA artifacts is needed. Now let's explore the specific implementation options for each programming model. For Python developers, the HANA ML library is recommended for interacting with SAP HANA Predictive Analysis Library and Automated Predictive Library algorithms. Reference code includes SAP BTP AI best practices sample code and SAP community blog posts like outlier detection by clustering using Python machine learning client for SAP HANA. For SQL developers, direct invocation of predictive analysis library procedures through SQL script is available when embedding logic within SAP HANA artifacts is a priority. Reference documentation includes comprehensive guides for device algorithms. Each approach provides full access to clustering capabilities while allowing you to work in your preferred environment. This Python example demonstrates implementing clusters. In particular, this example uses the k-means algorithm. This implementation showcases how quickly you can implement clustering with minimal code through SAP HANA ML. This best practice guide reflects the collective expertise of data science and analytics specialists from across SAP, bringing together insights to support your clustering tasks. Thank you for watching this session on clustering using SAP HANA Machine Learning. We hope the information provided helps you successfully implement effective clustering capabilities in your business applications.